Hello and welcome to HCI 509, Research Methods and Statistical Analysis. In this lecture, Lecture 8, we'll talk about the reliability of experimental results. Let's get started. We hear the word reliability often, and we have a good notion of what reliability is in our daily life. Think about what reliability is with respect to experimental design. What kinds of attributes are important to ensure that an experiment is reliable? Well, one thing that we know is that all research strives for high reliability. But what attributes are there in a reliable experimental design? Let me pause for a minute and let you think about this, and then we'll continue. So reliable experiments are ones that could be replicated by others. If you have conducted a research study with participants and you've detailed exactly the steps that you went through, others that follow the same steps should find results that are consistent, dependable, and stable, meaning each time they run the experiment, they should get the same results, and it should match what you have already attained with your experiment. With HCI, there's an additional challenge. Because we're measuring human behavior and social interaction, there's a lot more fluctuation in this than, say, measuring a computer's performance or measuring the performance of another type of activity, such as physical activity. Therefore, by nature of what we're measuring, our designs are less replicable than these others that we've spoke of. And the fluctuations, meaning the variance in the experimental results, these are referred to as errors. When we talk about errors, what we mean are statistical errors, not necessarily mistakes that you've made in doing this study. Let's talk about some types of errors. We'll start with random errors. What is a random error? Let's say we have a task and we observe a participant typing several text documents during 5 different sessions, and we obtain an actual typing speed of 50 words per minute. But it's very unlikely that they would get 50 words per minute each time they took the test. What's going to happen is you're going to see data that looks something like this. You're going to see some kind of variance between their performance on different sessions. And this is very normal, but you're going to notice that the relationship between the actual value we're looking for and the observed can be expressed like this. So the observed value is the actual value plus random error. So these could be considered noise. That's often how it's referred to. And sometimes you hear it referred to as chance errors. They occur by chance and they're not correlated with the actual value, meaning they're not consistent each time. They're as random as we saw in the previous example. Notice that there's not an additional time that's consistent in that error, meaning we expect 50 words per minute, but they weren't consistently above and below that, like by 3 words per minute above and 3 below. It was a random amount that was added or subtracted from that 50 words per minute that we had as the average. We push the observed values to move up or down around the exact values. Let's talk about how random errors can be mitigated. One way is by increasing the sample size. So while there's no way to eliminate random errors, we can reduce their impact by increasing the number of samples that we're working with. Let me give you an example. We have a coin, and we're trying to decide if it's a fair coin, meaning it's got a 50% chance of heads and 50% chance of tails. We don't know that at the beginning of the experiment. So we flip it twice, and if it's fair, we would conclude this if we get 1 heads and 1 tail. But the chance of exactly 1 head and 1 tail in 2 flips is it's pretty small relative to whether we can determine it's a fair coin or not. The only way we can really get enough information to make that determination is to flip it 100 times or even more. So as I flip that coin more often, the chance of it being 50% heads and 50% tails increases if it's a fair coin. So even if it's a fair coin and we flip it twice and we get heads both times, we might conclude that it's not a fair coin and is biased towards heads. Somehow there's some weight in the coin that can flip it towards heads. However, with two observations, it's simply not enough. We need to let the central limit theorem take over and let us see that as we flip it 100 times, we may have a percentage that's maybe 48 and 52, maybe 48 heads and 52 tails. This will allow us to see that there's more of a chance of it being 50% heads and 50% tails, which is a fair coin. With 2 flips or 5 flips of the coin, we're not going to be able to make that determination without a lot of error. So a small sample size, you can see that the random errors, say we flip it twice and get 2 heads, is going to have a significant impact on the observed mean. In this case, the mean of heads is going to be 100%. This might cause us to conclude that the coin is not fair when it actually is. A larger sample size, you can see that random errors are going to offset each other, and the observed mean, in this case, it is an actual fair coin, it should be very close to the actual value. So it should be, with 100 flips, we should see it pretty close to 50% heads and 50% tails. So let's go back to that example we talked about earlier. We had 5 sessions, but if we just took that single first session, the mean was 46, which is 4 below the true value of 50 per minute. Remember, 50 was the average of 5 sessions. So if we increase the number of observed sessions to 5, the mean goes to 49.8, which is really close to the 50 that we expect, which is the actual value. So there's no perfect way to say that what we observe is the actual value. Even if I flip a coin 1,000 times, it's not going to be exactly 50%. The chance of it being close to that is high, much higher than if I flip it only twice or 4 times. But there's no 100% chance that it's going to be exactly 50%. So the larger our sample size is, the closer the observed value is to the actual value. So that's what the central limit theorem, which we'll talk about later, is allowing us to see. There's another kind of errors besides random errors, and these are systematic errors. So systematic errors are what we call biases. They're different from random errors because random errors cause variations in both directions around the value. So you can see with the typing example, sometimes I was high, sometimes I was low. If we took a streak of coin flips, heads and tails, say we took a random sequence of 10, there's a chance that maybe we would get 4 heads and 6 tails. And then if we took another set of that 100, we would see perhaps there's 6 heads and 4 tails. But overall, we can see that there's bias in either direction, and there's an equal chance of it. A systematic error pushes the observed values in the same direction. So they don't offset each other the way random errors do. Therefore, the observed mean might be too high or too low. Let's talk about why and what these systematic errors are. So remember that typing task. Let's just assume that the participant consistently underperformed all 5 of the observation sessions. Maybe they were tired or fatigued, or they couldn't focus for some reason. So then we get the following data set. Okay, so they do 5 different sessions, and the observed mean from these 5 is 44.8. And this is actually 5 words lower than their true performance. So if we were to map that with the unbiased conditions, the observed values fluctuate due to random errors, okay? The fluctuations go in both directions around the mean. You can see that solid line at 50, and you can see the blue line kind of hovers above and below that 50. The bias condition, it pushes all the values down, and that's where you see that magenta line. So the mean of the observed values is significantly below the actual value. I want to point out the danger in using the word significantly, because when we say that using a statistical test, we need to back that up with data. And we haven't done a statistical test on these 5 data points. So I would say that the mean of the observed value is below the actual value until we actually have a statistical test to show that. So the word significantly, we have to be very careful in its use because it has some kind of meaning that conveys a statistical difference that we have shown. Let's talk about how systematic errors can occur. They could be due to measurement instruments. They could be due to experimental procedures. They could be due to participants, and they could be due to experimenter, meaning the person giving the experiment, their behavior. It could be due to the environment in which the experiment's conducted. Let's talk about them one by one. So with measurement instruments, these could introduce bias because they could either not be calibrated correctly. So if you have a measurement instrument that's not appropriate, say you're trying to measure how far you throw an object, and you're just using a way of measuring, and that's by using pace. So you're actually walking and you're trying to guess at how many feet or meters that particular object got thrown. That's not really an appropriate measure, because if somebody else does this experiment somewhere else, they may not have the similar gait as you, or another experimenter who takes over on a second day of the experiment for you may have a separate gait, and that's going to introduce some kind of bias. That also means that it's not accurate, or it could not be configured correctly. I use a lot of eye tracking devices, and one of the problems is they need to be calibrated. And when they're not calibrated, it's very difficult to know this until you're well into the experiment. So the calibration takes some skill. And if it's not calibrated correctly, it can introduce bias. So we need to make sure that the instruments are carefully examined. Another one is to use software-driven instruments, because later on, if we do this experiment and we find that there's some kind of bias, we can make some kind of adjustments. And typically, they have been tested really well, and they're reliable, meaning they are known to be accurate. So they may also avoid human errors in some cases. Even in measurement, I do a lot of research where we're measuring or counting the number of bugs in the rice field. And it's a very tedious type of activity, meaning we don't have a machine to calculate this. We have somebody who is in an uncomfortable situation out in a rice field, and they have to count quickly, usually because we have to make these measurements very soon before dark. And they have a limited amount of time, and there's quite a bit of human error involved with the counting. Now, this is not an HCI experiment, but there's similar challenges that we might encounter. So one is using a stopwatch to measure the time it takes for a participant to locate an item on a website. Let's just say we use a stopwatch or we use something on our phone. It takes time between the time the person begins and the time the finger actually hits the device to start it, and also when it stops. And this becomes an unreliable aspect of the measurement. And let's just assume that the stopwatch is not accurate. Let's just say It misses 5 minutes in every hour, which is a very unreliable stopwatch. So it's going to undercount the time. And then the actual performance is going to be better than the actual value. So if I say, here's a Where's Waldo book. Let's see how many times you can find Waldo in an hour. But the actual measurement is 55 minutes instead of an hour. It's going to undercount the amount of time and the number of times that person or that subject found Waldo in the book is going to be over 55 minutes instead of an hour. So their performance is actually going to be better. So let's talk about some experimental procedures we can follow. Sometimes bias is much easier to remedy than using the measurement instruments. And one way is if there's inappropriate or unclear experimental procedures. And this happens very frequently. The instructions that participants get play an important role in whether there's bias. So the wording of the experiment instructions should be carefully scrutinized. Also, a study supervised by multiple investigators is more likely to have an inconsistent message as instructions given to the participants. So it's better to either write or pre-record instructions and procedures to ensure consistency. You and another person are giving an experiment. The other person has a different personality than you. When the subject asks, can I do this? Can I use my calculator to the experiment? You say, well, I guess why not? And the other person says, no, absolutely not. The people who take the experiment under you are going to have a different set of instructions than somebody who goes through the experiment with your co-investigator. So here's an example. In a reported HCI study, under one of the experimental conditions, participants were instructed to complete the task as quickly as possible. And then in another condition, they were asked to take their time. There's no rush. On the no time stress condition, they actually completed the task faster than those under the time stress condition. This is kind of a surprise, right? Because when people have stress, it can actually affect their performance in a negative way. The critical wording of instructions is important. Additionally, the instructions that participants receive also need to be consistent. Now, this can be a challenge when you have participants who ask questions, because questions may not be scripted, and your response, you being the experimenter, may be different each time. Or you may notice something with the first participant and give additional instructions to the following participants based on some of the questions the first participant had. So this can affect the bias of the experiment as well. The first person may not do as well as the second or subsequent participants. So how do we mitigate these? Well, one way to do this is to randomize the order of conditions, tasks, and scenarios with experiments that adopt the within group design. Remember, the within group is where you have one subject doing multiple steps of the experiment. Remember, we talked about the Dvorak, the QWERTY, and the alphabetical order keyboard. We want to make sure that we vary which one they use first, and maybe vary the scenarios in which they're using those keyboards. We talked about transcription and composition. We want to prepare a written document with detailed instructions for participants. If you have a lot of participants, it may be better to actually record a video so that they don't have any kind of additional bias, because if you're reading instructions one time, the first time, maybe you have excitement. This is the first time you get an experiment. This is the first time you're actually running the experiment. But after the 50th time, you're going to be tired of reading those instructions to the participant. Also, you might want to have a written document for experimenters. One day you may not be able to be the one running the experiment, or if you might run it with multiple partners, they need to know exactly what you need to tell the participants. Sometimes you can't answer the questions. So if they ask questions that will bias the results, you have to keep quiet because you didn't give that information to previous participants. That information needs to come across to other experimenters so they're not guessing and giving additional information to others when they are participating in the experiment at a different time with a different experimenter. It helps to run multiple pilot studies, so this helps identify biases. Now, this takes time. We typically have deadlines, whether it's submission of a paper or we're trying to finish a course. So it's important to run smaller pilot studies if possible before actually doing the data collection. So you can see some of the problems you might run into with the questions that people ask. And if other experimenters give these instructions, do the participants have questions? So pilot studies are good at identifying bias. I run pilot studies whenever possible, especially when I do things with crowdsourcing. So let's talk a little bit about the participants. So the characteristics of participants can really introduce a lot of bias. This might be because they're in a specific age range. They have different levels of experience. They may have more knowledge in a certain field, or they may have better education, or maybe they've run experiments themselves so they can know what is expected and others may not. They may have personal interests. The tasks may be more interesting to some of the participants than others. Here's an example. An experiment to test a user interface of a new mobile phone. So they're recruited by posting announcements on a blog that features highly technical information. And its visitors normally have a strong technical background. And the consequence is the observed data would outperform what we would observe from the general public. I want to caution you here because in many cases, especially in graduate programs, we typically get other graduate students to help as participants in our studies. The important thing to remember is we want to have a sample that's representative of the overall population. So our graduate students, especially ones that are focused on IT or HCI, are they particularly good examples or samples that were representative of our general population? They're typically not. What this means is you need to be very careful with the external validity. So this means when you have graduate students who are taking and participating in an HCI study that are HCI graduate students, it's very dangerous to say this is a representation of the overall general population. You either have to reduce what that population is to say graduate students, or you have to get a wider sample of participants in your study. So here's some ways in which we can mitigate this. Again, we want to make sure the participant pool is representative of the target user population. And we want to make sure we create an environment that does not induce stress. It's helpful to say you're testing the interface and not the people because people get frustrated if they're not performing well. They don't want to look bad and they don't want to embarrass themselves or the experiment. It's perfectly fine if you want to reschedule a session or give some participants some time to recover if they are arriving and they're not really in the mood to do their best performance or they have a lot of stress. Another thing that we need to consider is experimenter behavior. So this is one of the bigger sources of bias. So intentional action to influence performance, unless it's a deception study, is unethical, and we should avoid that. So we shouldn't try to induce stress to test out stress unless it's been fully vetted by the IRB. It's amazing how spoken language or body language or facial expressions can be conveyed as either positive or negative to people participating in the experiment. Let's give a scenario. So we have an experimenter who's introducing an interface to our participant and says, now you get to the pull down menus. I think you'll really like them. I designed them myself. Well, the experimenter is very demanding. The comment may make the participant reluctant to provide negative feedback in case the experimenter's feelings are going to be hurt. So what's going to happen is the data collected from the participant, especially subjective feedback, is likely to be better than the actual value. So if you're taking a Likert test to say how exciting this particular video is, and I'm standing right over your shoulder, you're typically going to rate it more highly than you would if you were doing it anonymously. Here's another scenario. An experimenter is loading an app for a participant. The response time is a bit long. The experimenter is frustrated, says, damn, it's slower than a snail. Here's another one. An experimenter is loading an application for a participant. The response time is a bit long. The experimenter waits uneasily, tapping the fingers on the desk and looking very frustrated while staring at the screen very impatiently. Experimenter's spoken or body language reveals a negative attitude towards the application. And participants would register those cues, and their perspective would change to negative even before they encountered the app. So the subjective ratings and feedback would be biased against the application. Here's a third scenario. A participant arrives right on time for a study scheduled at 9. The experimenter doesn't arrive until 9:10, and then after guiding the participant into the lab, the experimenter takes 10 minutes to set up all the equipment. This happens quite a bit. Once the experiment starts, the experimenter finds that the task list is missing and runs out to the lab to print a copy. Not very professional. So the unprofessional and kind of relaxed style of the experimenter gives a negative impression to the participant, which may impact the participants in performance, as well as the subjective ratings and feedback. We need to offer training to experimenters and teach them to be neutral, calm, and patient. We want to have the experimenter arriving early and make sure everything is ready, maybe have a checklist, prepare the written documents with detailed procedures, and require all experimenters to follow the same procedure strictly so we can avoid bias. And then when appropriate, it's better to record important instructions before the experiment and play the recording to the participants during the experiment. Why? Because if we record it, everybody's getting the same visual and vocal cues. So this way we can standardize the training process and also the instructions given to participants. It's nice to have two experimenters in the same session. So one can serve as the lead and the other can serve as the assistant. So the lead is responsible for interacting with the participants, and the assistant can make observations, adjust for errors, and take notes. So the experimental environment is also important. Environmental factors are more important now than in the past because we're doing things in mobile computing, we're talking about accessibility, and also we're using things that require recognition. And these frequently involve environmental factors. So you're doing them out in the wild. So they can be categorized into two groups. There's physical, noise, temperature, lighting, vibration, and humidity. And then there's social, like how many people are in the environment and the relationship between those people and the participant. So these can introduce systematic errors as well. Think about how physical noise or temperature or lighting or the vibration, let's say you're in a laboratory environment, all of these can introduce forms of stress or reduce the ability for the participant to focus. And then in social, you can just imagine if there's a lot of people around, there's a lot of distractions, and maybe the relationship between those people and the participant can affect that as well. So here's an example. If you're studying the performance of speech recognition, it may have lower rates if there's a significant level of ambient noise during the session. ambient noise can interfere with a participant's ability to hear certain aspects of the task, or they may be distracted by what they hear in the background. So loud environmental noise may distract the participants or induce fatigue. Now, should you always avoid this type of environment? No, because if you are trying to use a particular device that needed to be robust in a sporting environment or at a concert, you don't want to avoid the physical noise that we're talking about here. However, in most cases, if we're just looking at the speech recognition application, then it's better to do it when there's less ambient noise. Also, think about if you were taking a test and somebody, say the instructor, is standing over your shoulder and they're watching what you're doing. Now, this is going to affect how stressful the situation is, and it's also going to affect how you participate relative to if you had a nice, quiet environment where you're being observed at a distance. So these kinds of environmental factors can cause problems when you don't have a lab setting. So let's talk about how we can mitigate these. In a lab setting, it's obvious. We want to make sure it's quiet, good lighting, everything is comfortable, clean and tidy without distractions. And whenever possible, you should try to seat them so that they're not feeling like they're being observed. So this could be from another room. And in a field study, you should visit the location first to make sure that the setting's going to be appropriate. So in conclusion, biases cannot be eliminated. We can try to mitigate them, especially those that we have control over. But a well-designed experiment with lots of consideration for controlling bias can improve the data. Now, one of the frustrating things when you get to writing papers is when you design an experiment. There's always going to be that one person who's reviewing your study, and they're able to pick out something that you have had that could possibly introduce bias. Now, everything we've talked about here are ideal. And you're going to find that in an environment where you don't have endless time, endless money, and the ideal participants, it's going to be very difficult to completely control for these biases. However, if you show that you've made an attempt to control for the major ones, and what the major ones are the ones we talked about here, then it goes a long way to show that you've got a well-designed study and the study is controlling for bias the best way that you know how to do. So the observed results are going to be closer to the actual values, but those biases just never completely disappear. So when you're reporting the findings, sometimes it's good to say some caveats about what you're finding. If the results show statistically significant value differences, say with a treatment and with the baseline, what's going to happen is you need to be careful when you report them, and you need to identify what potential biases you are unable to control for, so that others later on reading it are not going to poo-poo your report, even though you had no ability to control for those, for example, ambient noise. Thank you, and I hope this has been helpful. I'll see you next time.